Hello guys, thank you so much for being with me in another artificial neural networks tutorial video. In this video we want to talk about other methods of updating weights parameters. In some cases these methods give us answer faster. In addition, we will see another powerful method for regularization. First, we start by updating the parameters. In this loop, we consider a bunch of data. We calculate the loss function and calculate the gradients with the backward algorithm, and finally update the weights with the help of the learning rate. Here the slope of the cost function is steep in the vertical direction, but slow in the horizontal direction. If we take a step in the vertical direction, in these curves to reduce the cost function, we have a greater reduction compared to when we take a step in the horizontal direction. That is, the gradient in the vertical direction is a larger vector compared to the gradient in the horizontal direction. For this reason, if we use the gradient descent algorithm, we have an irregular and a zigzag movement in the vertical direction. Now, how can we solve this problem? We have irregular movements in the direction where the slope is high. We want to smooth these movements. We can do this very easily using the momentum method. In this method, the change of the direction is very gradual. The idea of this method comes from physics. If you drop a marble from the edge of a bowl, it will travel in a zigzag motion until it reaches the end. We want to prevent these irregular movements by creating a friction. The whole algorithm does not change and only the update line changes. We want to define a velocity vector. We define v as a coefficient of previous of v minus this friction. Friction is the product of learning rate and the gradient. That is, we must first calculate v and then add x to the v. At the starting moment, the velocity is 0. This mu coefficient is a positive number smaller than 1. At the start moment, we have a movement similar to the start moment with the gradient descent algorithm. In the directions where we have a large slope, friction causes the speed to decrease. In the direction where the slope is low, there is no sign of change. Changing the direction, so the speed is much higher. That is, the diagram of the momentum algorithm covers a greater distance in a shorter time. We can improve the momentum method itself. These theta parameters are the same parameters that we update. The idea of Nesterov's method is very simple. It says that you know the direction of movement, and you know that the change of direction does not happen now and then. So probably the direction of movement should still be similar to the previous direction of movement. That is, we make a prediction. There is only one problem that we used to calculate this gradient in backpropagation. But now we don't have the gradient of the loss function at this point. You know that the gradient represents the direction of movement. So by ignoring the direction of movement, we have actually ignored the gradient. To solve this problem, we use a variable change. The goal is to remove theta's and write the relation in terms of phis. These phi parameters. Finally, we get to this relationship. It is also very simple in coding. These small changes make solving real problems which normally took a year and now only takes a day. Another method is AutoGrad. In general, we consider gradients in n-dimensional vectors. So far, we are moving equally in all directions. And now we want to move more slowly if the slope is high. For example, the size of the gradient vector is large. And in the directions where the slope is low, increase the size of the gradient vector. That is, we want to have a suitable learning rate in each direction. For this, we calculated the sum of the squares of the slope in each direction. I have defined this as a cache variable. When the gradient is large in a direction, the cache value for that direction will be large. And if the gradient value is small in a direction, the cache value will be small in this direction. And now in the update, we will have a division by the square root of this cache value. And to avoid the problem of division by 0, we will add a small value to it because the cache size is 0 at the start, at the beginning point. This method is not necessarily always better than the conventional gradient descent method. It depends on the issue and the problem, you know. What is wrong with this method? This sum of squares is constantly getting bigger. As we move forward, this learning rate keeps getting smaller and smaller. That is, the step size keeps getting smaller. How can this problem be solved? It is very simple. Use the RMSProp method. In this method, instead of summing with the square of the value of the gradients in updating the cache, first multiply the cache by a parameter smaller than 1 so that the cache is slightly smaller. Then add the value of the product of this cache in this parameter with the product of the square of the gradient in the product of the difference of this parameter from 1. You can see the relationship here. You can see it here, this formula. In fact, we do an interpolation between the previous cache values and the square gradient and prevent this value from increasing. The last updating method is the Adam method, which is usually used in deep neural networks and is a combination of RMSProp and a momentum method. In this method, we first calculate V using the RMSProp method. In fact, this method uses the statistical concept of weighted average, weighted mean. Here, M is the weighted average between the gradients. The code of this Adam method is not so simple. We consider M and V to be 0 at the beginning, and for this reason the updates face a little problem. That is, very small values are calculated for M and V in the first iterations. This problem continues until M and V reach suitable values. In order to help this algorithm to reach this appropriate value sooner, we add a correction value to them. For example, in the first iterations, we can divide these various small values by numbers between 0 and 1 to make them a little bigger, a little larger. When they are large enough, they are big enough, we stop doing this. This stop happens due to frequent exponentiations of fractional numbers smaller than 1, which is desirable for us. T here is the same number of repetitions. Okay, thank you so much for watching this video. We will have 2 other videos, and I highly recommend you not to miss them because of the very practical and useful tips inside them. Have a nice time.